Hi everyone. Okay, very successfully and very nicely doing questions and theory all together, we done with Unit 4. What is Unit 4? I have done Unit 4 for 2027 students and we are done with the Unit 4, so that I thought of doing this little summarization for Unit 4. Unit 4 is the gaseous state of matter. We're going to talk about all these gas laws for gases. But we have a little problem because there are lots of different gases which are having different properties. So what can we do is we are using this imaginary gas which we call the ideal gas, which there are no intermolecular interactions, which there are no volumes, so we call them the point masses, and there are no kinetic energy changes, so their collisions are perfectly elastic. Such gases are called these ideal gases. So all these gas laws are based on these ideal gases. Okay, to understand the ideal gases, we are using this little equation, ideal gas equation. In that, you know the P pressure, V volume, N number of moles, T is the temperature, but the new term comes, that is the R gas constant or the universal gas constant. There are different units for ideal gas constant. So we did calculations to understand what is this R, and also for to find other four terms in this ideal gas equations. That is the very first part. After that, we move to find these other equations or the other laws derived from the ideal gas equation. So using the PV equals nRT, we can derive 6 gas laws. Out of those, 3 are in your syllabus: Boyle's law, Charles' law and Avogadro's law. So we have 4 different gas laws so far: ideal gas, then Boyle, then Charles and then Avogadro. Out of that, the very first we did was the Boyle's law. In Boyle's law, pressure volume is having inverse relationship. To understand that, we did calculations, plus also we did these connections between each other. When there is this inverse relationship or the direct relationship, what is happening? So the volume pressure having the inverse relationship, so you're going to get this hyperbolic curve. If it is a direct relationship, it is a straight line going through the origin. If it is a constant, then it is a parallel line to x-axis. Okay, that's all with the Boyle's law. Then we moved on to the Charles law. Charles law is the one that we talk about when the pressure is constant, volume and temperature is having direct relationship. So the volume ratio is supposed to be equal to the temperature ratio when pressure is constant. To understand that, we did questions, and also we had other equations derived from this Charles law. So we did that part, and also we did couple of these graphs again. Again, if they are having normal direct relationship, we're going to get this normal y equals mx, a straight line going through the origin. But since if there are like, you know, this constant relationship, so we are getting this parallel line which is parallel to x-axis. So that is all with the Charles law. Then we talked about this perfect crystalline solid, absolute zero, those equations, we did all those. So this is our third equation, that is for Charles law. And then combining Boyle's law and Charles law together, we went through this what? Combined gas law. In combined gas law, we again derive this little connection for calculations. When all these three, pressure, volume and temperature, are varied, how do we find one of these unknown terms knowing the other 5 terms? To understand those, we did a lot of questions again. Then we move to Avogadro's law. Remember, in Boyle's law, boiling temperature, so the Boyle's law, temperature is constant. Charles law, the other one, which is the pressure constant. Then the combined gas law. Pressure, volume, temperature, all are varied. Then we are moving to Avogadro's law. In Avogadro's law, both pressure, temperature, constant. When the pressure, temperature constant, volume is proportional to number of moles, and also pressure, temperature, volume. If all these three are constant, number of moles are exactly same. And we did calculation to understand all those principles. Lots of calculations we went on. Actually, that is all. Okay, Peacock and me. That's all the gas laws in the first or the initial part of this unit. So this unit has two different parts as I have explained you guys. The first part we're going to go with these gas laws, and then the second part is to understand behavior of these gaseous molecules. To that we have this one single graph. We call it the Maxwell-Boltzmann distribution curve. Okay, gas particles are moving randomly, continuously. So, zero molecules is having zero energy. So, all the molecules are moving. And the gases are the physical state which is having the highest kinetic energy. So, that the graph is not symmetric. It is dragging more towards the right side. So, we're going to talk about everything. At the same time, we talked about different properties of this. To understand that, we did 4 different speeds. Most probable speed, mean square speed and root mean square speed. To understand all those, we did couple of questions and we did couple of calculations. Then what happened when we are changing different parameters, we did all those as well. And then another last little part is the kinetic molecular theory. There are 6 assumptions in kinetic molecular theory. Under that, we had this third one. Square volume summation supposed to be equal to each other. To understand that, we did questions as well. And then we moved into kinetic molecular equation. Kinetic molecular equation is for one single system, per one single molecule. Because earlier we talked about taking the system as a one single thingy, but here one molecule is as a one single system. Earlier we talked about one whole system as a one single unit. Here, one molecule or the one particle is the one single system. So that here, PV equals 1/3 mc squared bar. Here, m is the mass of the one single, whatever the particle, gas, molecule, gaseous atom or whatsoever. Okay, using this one, we are showing the connection. Average kinetic energy depends, or the kinetic energy depends only on the temperature. We can derive this equation, E bar equals 3RT over 2. And plus, again we can show and we can derive this another little equation. Actually, I want to introduce you guys this Boltzmann constant as well. Kinetic energy equals 2/3 kb into T. You guys need theory to understand this. Plus this part, trust me. Even when I was doing this, I was feeling like they were not asking these questions for a couple of these recent years. Then all of a sudden, the last year exam, the very fresh exam in 2024, they were asking how would you derive this little equation. Actually, in this class, we derived 3 different equations starting from kinetic molecular equation. The very first one is C squared bar equals 3pb over m. And then the second one, C squared bar equals 3p divided d, density. And the last equation, C squared bar equals 3RT over m. Okay, they are asking questions out of this part, calculations, so that you guys have to practice how to derive these plus doing calculations. Anyone who is listening this, who has done this 2024 A-level exam, and who were with me, they know how I emphasize all these, and they were feeling like it's really nothing when they ask these questions. Because we got a proper practice. We did that actually. So that to get the practice, we did lots of questions here. And then, so far we talked everything regarding ideal gases. So but in real life, we don't have ideal gases. In real life, we have real gas. How would you use these ideal gas equations to real gases? Ideal gases are having no intermolecular interactions. But real gases are having high intermolecular interactions. Ideal gases are having no volume, but real gases are having high volume. Ideal gases, kinetic energy is constant, so the collisions are perfectly elastic. But in real gases, collisions are not perfectly elastic. You guys know they are also making products, reacting chemically with each other, so the kinetic energy is always changing. So these 3 are the differences between real gases and ideal gases. How do you convert real gas to ideal gas? Okay, real gases are having intermolecular interactions. So what can we do? We can Cancel the intermolecular interactions. How? When molecules are getting away from each other so badly, then what happened? There are no chance of getting contact with each other, so the intermolecular interactions are getting down. So what we can do? We can increase the volume by decreasing the pressure, or we can increase the volume by increasing temperature. So those two are the methods that we can convert real gas into ideal gas, by increasing temperature and by decreasing pressure. Kinetic energy increasing, molecules moving faster, so they are not getting chance to make intermolecular interactions. And even when the volume is larger, then the particle size becomes smaller comparing to the size of the container. So that using those two methods, we can convert real gas into ideal gas. So that they have proposed us two different methods that to understand ideal behavior of real gases. For that, there are two different criteria they are using to understand the behavior of real gases. The very first one is the compressibility factor. It's very easy to understand. Very easy to understand. What is the compressibility factor? Compressibility factor is the ratio between PV and nRT. So that you guys know PV equals nRT for ideal gases. So that PV divide nRT become 1 for ideal gases. And let's say this is a real gas. In real gases there are either attractions or either repulsions. Let's say the attractions are greater. Then the volume becomes less. Molecules get closer to each other. PV become less. So that PV divide nRT become less than 1. So compressibility factor is less than 1. And the other way around. Let's say they have the repelling property. Repulsions rejecting molecules each other. Then what happen? Repelling from each other, molecules get away from each other so that the volume is now high. So that when the volume is high, V is greater. So PV is greater than nRT. So the compressibility factor becomes greater than 1. So for real gases, PV is unequal to nRT, so that the compressibility factor can be either greater than or either less than 1 comparing to real situation. Okay, so that these are the two different conditions. Compressibility factor is greater than 1, PV is greater than nRT, so PV divided nRT is greater than 1, PV is greater than 1, repulsions are greater than attractions. And then the other way around, let's say the compressibility factor is less than 1. Then what happens? Compressibility factor is less than 1. PV is now smaller. So that PV is smaller than nRT. PV smaller means repulsions are less comparing to attraction. Now the attractions are greater. Molecules get closer to each other so that you can easily compress the gaseous samples. Okay, so how it is behaving with the higher pressure and the lower pressure depending on intermolecular interactions. Then we talked about that part. Then the last little thingy, when we talked about this Van der Waals equation. This is the second criterion that we discuss the behavior between ideality and real gases. In ideal gases, we have P, V equals nRT. But in real gases, since they are having a less pressure, we're going to add a part of pressure. Since they are having a more volume, we're going to remove a part of volume. Why this is happening? Go through the note, go through the theory, so you can understand that better. Once you go through the theory, you can understand this better. Why we are adding a part to pressure and why we are subtracting a part from volume. Okay, so that is the last little part. That how do we recognize or how do we define these real gas using these ideal gas equations. Other than that you guys have this little thingy again, I was given a little explanation. What is this critical temperature, critical pressure and critical volume, triple point and so on, which is really extremely important for equilibrium, your 12th unit. Then you have last two these experiments that you're supposed to do. The very first one is the determination of molar volume of oxygen. And then the last one is the determination of molar mass of magnesium. Okay, see how easy to understand unit 4, how easy you can go on with that. But since you already having the memory, while you are having the memory, just try to do the full tute, and then you can go with the tute reviewing, and then you can fill your notes as well, and the tute as well. And I want you guys, like I'm just saying every day, I'm just saying this again, once you're done with your tute, your understanding become different. So the way you already understood, and after you doing the tute, you are understanding the same theory is different. Then I want you to add your new view to your theory note. Go through the theory note again, and whatever you got from this tute class, then you have to add to the theory note, then you can make the perfect theory note. That's all with the gaseous state of matter. Let's meet soon with the Unit 5 energetics.